And the Maxwell formulation using quaternions was used for some time. Then another ingenious physicist, Heaviside, or mathematician, physicist and mathematician Heaviside, formulated those equations in the way we know them. And we call them Maxwell equations. But this formulation does not come from Maxwell. Now let us do that. Those equations could be formulated in two ways. One is integral, the other is differential. We can convert that using Stokes' law or Gauss' law so that those things are equivalent, but anyway, it is important to know at least one set and the mathematics behind, or both sets, and then use them. So I will start with one equation we have already formulated at the very beginning. That was the Gauss law for electrostatics. As you remember, we had a law that said that an integral over closed surface over electric flux density dot product with the element of the surface is equivalent to the charge that is contained within that surface. Well, let's formulate it a bit more precisely. The total charge within that surface could be obtained if we count or add all the charges inside, which means that we carry out an integral over the volume of the charge density times volume element. So it then gives you an integral of the charge density over the volume, and the story for this is that this volume is contained inside this closed surface. So yes, this is, we already know from the Gauss law. So this is one of the Maxwell equations. Then we have another equation which is very, very simple. And this equation now is we have an integral of magnetic flux density over a closed volume, over a closed surface, and this is really simple because this integral is always zero. So we have the second Gauss, or the second Maxwell equation in integral form. So those are those two equations that tell us what happens with integrals over a closed volume. In electrostatics, we have got some flux, or we can have flux that flows out or in, depending on the charge inside. In magnetic field, there is no flux because all flux lines are closed. We do not have a magnetic monopole. Unlike with charges, we have a monopole, a positive charge. We have the other monopole, negative charge, and the flux line runs from positive charge to negative charge. But in the case of magnetic field, a flux line is closed loop. So those are two Maxwell equations. Now the others have something to do with integral over a closed path. So those are integrals over closed volume. Now the closed path integrals. So if we have an integral of through a closed path of the magnetic field intensity times the element of that path. We already know that. This is the left-hand side part of the Ampere's law. So we know that there is current on the right side. But, well, okay, we can put it down in somehow more organized way. What a current is, we already know that. A current could be obtained by integration of current density over the cross-section of the conductor. So what we can do is that we write it in this way. It is an integral over a surface, and I will tell which surface. And so we would get an integral of J, current density, dot product with the surface element. Now we integrate through a surface, and this surface is connected to the integration loop. If we had the loop like a frame for a drum, and we would put the membrane on it, like creating a drum, then the surface would be the membrane of the drum, which is tightly connected to the frame, to the loop. So any flux, any current flux, which is called electric current, through that loop or through that membrane would count here to the total current. So yes, we know that's the current. Let's leave it for a moment like it is, and let us put down another equation, which in fact is the induction law. We know that an integral over a closed loop of electric field strength dot product with the element of the loop should give you the voltage induced into that loop, and that is minus the time derivative of the magnetic flux flowing through that loop. So but we can again put it down in a more organized manner. So it would be minus the time derivative, and inside that time derivative there would be an integral. To obtain the total magnetic flux, we should integrate flux density dot product with the element of the surface over the surface. So we would have here B ds. So again, there is the same story. We integrate over a surface which is tightened to the loop like a membrane to a drum. So we get all the magnetic flux that runs through that loop. And now this is also a time derivative of the magnetic flux. So this would be the induction law. We can make it more precisely, calculate it more precisely using this notation. But it means the same. Now, I have shown you 4 equations. Of those, 3 are Maxwell equations, and 1 is an incomplete Maxwell equation. And to tell you about that, I would for a moment use this space over here to tell you a story about a strange kind of current. So far we have been talking about a current which in fact means moving electrons within conductors. We can easily understand that moving protons would be of the same importance, but that means moving the mass. Let's skip antimatter with positron and antiprotons, but moving those charges would raise a current. Is that the only way how to do that? Is there any possibility to do something which has the same effect like a current without really moving anything at a long distance? I mean, we don't care electrons revolving around the atom nuclei. They are moving, but they are moving on a closed loop. If we get Bohr's model of atom, at least. So, is there any possibility to have some meaningful current that would give rise to magnetic field without moving anything? Now, I skipped the long distance, so without moving anything at a short distance. And the reply is yes. Let's look into a piece of dielectrics. Let's say, let's have a cup of water. Well, the cup of water consists of an enormous number of water molecules. Such a water molecule more or less looks like a big atom of oxygen, which is, let's say, 16 times heavier than an atom of hydrogen. And due to the nature of polar forces, we can roughly draw the molecule of water like this. It's not perfectly symmetric. Those two protons are not on the other side of the oxygen. So in fact, as the molecule is highly polar, in fact, the oxygen steals electrons from those protons close to completely. We have two positive charges over here and two negative charges within here. So what we have, if we look from a longer distance, is something which is of an elliptic, say, shape, and it has got a positive and a negative side. Now, if you have a cup of water without the presence of any field, those molecules are disorganized so that their total electric field vanishes. But what if you apply some field from outside? Well, then, of course, positive sides are attracted to negative charge outside, and the negative sides of the molecule are attracted to the positive charge outside, so that if you apply electric field strength to some layer of water, some of the molecules tend to organize and to turn, so that now that situation is a bit different. Before we had this organized set of molecules, and now they tend to have some prevailing orientation. Well, okay, but now let's forget that a little bit and let's watch what happens on the ends. So let's think that we have somehow organized a brick of water which for some reason keeps the shape of a brick despite of any forces on the surface of water. So we have a brick of water which we put to a place with imposed electric field. So what would happen, in fact, we have the brick of water, we have some field from outside, and if we watch what happens, so at the beginning, with no field, with no external field, we have those two surfaces where there are some positive charges and some negative charges protruding out. So at the surface we have electrically neutral surface with some composed of some positive sides and some negative sides of those water atoms. Sorry, molecules. But now if we imply the field, those atoms or molecules tend to turn. So that, for example, the positive charges would accumulate here and the negative charges would accumulate here. Now this is a very small movement. We know that atoms are very small objects. But anyway, if you impose the field, generally those positive charges move one way and those negative charges move the other way. So there is, if you had a cross section anywhere, you would see a charge transport through that cross section. Or you can see at the surface that the situation has changed. When there was no external field, we had the same number of positive and the negative charges on the molecules just at the surface. And if the field is applied, suddenly we can see more positive or more negative charges that lie on the boundary. Which means that we are moving charge by the external field. We are moving it on a very, very short distance. The distance is so short that it, in fact, is not measurable or is not within the scope of the subject. But what we can see is that there is a moving charge. In fact, there is one charge, positive, moving one way, one negative charge moving the other way. We count both of them as they cross the cross section as some charge transport. So if we put this piece of dielectrics into a field, there is a charge transport at any cross section. But it happens only if we put it into a field or if we change the field. Then those charges are moved, the field has obtained a new equilibrium, and there is no more movement, at least from macroscopic point of view. So in fact, this is somehow a kind of electric current that happens only if there is a change in the electric field, in the polarization. And this current, more or less, is given by a small displacement in the location, just the molecule which is very tiny just turned. So it is a very small displacement, and therefore this current is called displacement current. And the amount of the displacement current is given by the time derivative of electric flux density. And therefore, we would have to add here so here inside the equation we have two parts. We integrate electric flux density, conductive current, and the time derivative of electric electric flux density, time derivative of electric flux density and the flux density itself. So we have two currents. This current integral J ds is called conductive current, and the other one is called displacement current. Now this hypothesis done very early was very important because the presence of displacement current makes possible any electromagnetic waves. Later, Hertz has demonstrated there might be waves, and in fact, introducing this into the equation gets the possibility to have radiation, electromagnetism in electrodynamics like waves. It gives the rise to a possibility to have light. So it's an important part of the universe. Although it's very, very tiny, it is very important. Now, we should then learn another topic. I will rewrite all those equations into a differential form. But before I do that, I will ask you for questions. I just look into the chat. So, okay, no questions loudly, no questions in the chat. So I will now go step by step, equation by equation, and formulate it within a point form or differential form. There are two names for the same situation. While those equations handle some finite volume or some finite sized loop, the equations in the point form handle the behavior of electric, magnetic, and electric flux field within a point. So, how would the first equation look in a point form? What you possibly remember the story we have been talking about to get divergence by limiting the surface close to zero. We would get divergence of electric flux density here and only the density of free charge here. So what we will obtain for the first case is that the divergence of D is equivalent to charge density. Now I will put it down in two notations. Some of you may like one, some of the other. So we have a nabla dot product with D, which is also referred as divergence D, and that is equivalent to the density of electric free charge. Now, this was the first equation in dot form. Which was the second here? We had an equation on magnetic flux density. It is very simple, but anyway, I will put it down. So the second equation reads that the divergence, which can be calculated as nabla dot product with B, is 0. Let's switch to other two equations. Now we have this equation, which in vector form or in integral form comprised an integration of magnetic field strength, magnetic field intensity over a closed loop, and using Stokes' theorem we could convert it into a notation which looks like this. We have nabla vector product with H that's it. And on the right side we would have densities of flux, that is electric current, which is the density of flux of charges, conductive, and displacement. So the right side, I just add that this is called circulation. And it is equivalent to electric current density J plus the displacement current, which is a derivative of electric flux density D against time. So this is the complete notation in dot, in point form, or let's say in differential form, of another Maxwell equation. Now we miss only one more equation, which is the equation so on the left side we have the circulation of the electric field strength, and this is minus the time derivative of magnetic flux density against time. So now here we have four Maxwell equations formulated for a point. This form is sometimes called point form or differential form. Four important equations. Just to remember, we have a set of auxiliary equations that are called auxiliary Maxwell equations. We have already been working with all of them. I will just put them down over here within a stationary, isotropic, homogeneous, and linear media. We have magnetic flux density B being directly proportional to magnetic field intensity H. We have the electric current density J being directly proportional to the electric field strength E. And we have the electric flux density D being directly proportional to the electric field strength E. Now B, H, J, E, D, and again E are vectors, of course, and based on the assumption that the material is homogeneous, linear, and so on, those are scalar constants. We call those constants material properties or constants, and this is permeability, this is permittivity, and this is electric conductivity. So we have a set of auxiliary equations. I name them just because we will use them later today when we will start to talk on electromagnetic waves. Now, your questions, please. Just a short remark. This and this, I mean, the formulation with nabla, or just simply writing divergence of B, are equivalent equations. So if I ask you, do you know the Maxwell equation which has on the right side free charge density, it is sufficient to write this or this. So I have done that because some textbooks like this notation and some textbooks like this notation. The law is still the same. Now, if there still is no question, I would start to work towards an equation that is called a wave equation. That was an ingenious hypothesis that has been obtained in the way we are going to do that. I mean, first, there have been some people handling Maxwell equations, and they have found a solution of that which seemed that there might be waves of magnetic and electric field propagating through space. But they had no means how to detect it. Only quite later they have constructed a thing called coherer, which was a thing that was capable of detecting electromagnetic waves. And then, in fact, first transmission has been realized. It has been sent by a spark and received by this detector. The story is quite similar to gravitational waves, which had been predicted by Albert Einstein and detected only 4 years ago by great infrastructures that are capable of detecting very tiny gravitational waves. So anyway, let's find out how to get the equation which is called wave equation out of Maxwell equation. So we will see how they did it centuries ago and predicted electromagnetic waves that have been later found out and that have been more or less mastered by us because we are able to use them for data transmission. We have very clever transmitters, very clever receivers, so we know how to handle electromagnetic waves. And to do that, we have to understand the mathematics behind it. So I will start to get something which is called wave equation, and I will use two of those equations mostly. So those two equations that continue circulation are of major importance. Now, I will use them in a way, or I will do that thing with something which is called an artificial step. what an artificial step in mathematics is. Well, normally you have standard methods, like you know that if you solve an equation, you can add the same number or the same letter, the same thing to both sides. By adding the same amount to both sides of an equation, the equation still is valid. You can even divide both sides by any number distinct from 0, and again the whole equation is still valid and unchanged, more or less. It has the same solution. That's the important point. But this is a set of mechanical steps that today are completed by MATLAB, MATCAD, Derive. So you have an automated algebraic systems that can solve equations. And then there are some tricks that have been invented that do not fall into those standard rules. That's an artificial step. Possibly somebody has tried to do something strange with the equation and finally he got the result. And one of those steps is here. So what we shall do here is that we will apply again a vector product from the left side with nabla operator, or we will make a circulation of this. So we will have circulation of these equations. So there will be again a nabla times this and a nabla times this on the right side. So let us do that first to find out what happens. Now I will rewrite both two equations.